village that can see all the way over the horizon to see the troops or the elk walking by because nobody else can, or almost everybody else can. So usually the concern is we can't see past a certain distance. We're looking out, and that, up close everything's fine, but there's a point where we can't see anything anymore. Beyond that, everything's blurry. And then beyond that, you just can't resolve anything. Well, we call that point, visually from our eyes, we call that the far point. The farthest point that you can physically see with the human eye. Everything else inside of that is just what your eye does to adjust beyond that farthest point that you can possibly see. The human eye is a very interesting thing, but here's what I want you to think about. We're going to estimate what a healthy, properly functioning human eye ought to be able to do. Now, take your glasses off if you wear glasses. Can you see Mount Hood clearly? No. Well, you know what? Compared to the dimensions of our eye, for all practical purposes, Mount Hood is infinity. I mean, or the moon. If you can see the moon crystally, you're looking at about as close to infinity as you possibly can. You're talking millions of kilometers, and you're seeing it sharply. You may not be able to pick out a gnat's ass in a crater. That's a separate issue. Your ability to resolve is different. But the ability to see a sharp object a long distance away, like the moon, is an effectively infinity far point. And so people that have healthy eyes, we typically say that they have that they can see things at effectively infinity. So let's just look at a healthy human eye. And let's make a few assumptions. Again, we'll sort of take this little Greek approach where we just, everybody's going to be a little different, but let's just take sort of a normal person, whatever that means. It probably varies by 20% depending on, from Asian to African to Northern European, just by physically the dimensions of the size. So here's where I'm going with this. Now here's the human eye, approximately. And the dimensions of the human eye are very complicated. Or not the dimensions. The dimensions are actually relatively spherical. But the optics of the eye are very complicated because you have a corneal region, which is a little part that sticks out. The clear part, that's where most of the bending of the eye is. Sort of your base eye color. Then you have this fluid inside, and water bends light. So you have effective lens due to this region called the vitreous humor. And then you have a solid little lens that sits inside that's surrounded by little really fine ciliary muscles. And the point of that lens in there is as the muscles contract, it contorts or bends that little inner region of the eye. And that's how focus is adjusted. You've got literally a bendable lens. And as you get older, it becomes harder for that lens to flex. And if you have cataracts, that lens gets all coated. You can't see through it. But for all practical purposes, if you would treat the human eye as though it has a single thin lens, the approximate distance from the lens to the sensory neurons. The sensory neurons are functionally our little neuronal CCD sensor. Or if you will, it's our little light sensor that picks up focused images on the back of our retina. So back here on the retina, where the little neurons attach that sense the light coming in. So our retina acts as a projection screen, or like a little CCD digital camera, if you will. The distance between the lens and the retina is, like I said, it'll vary by at least 10% depending on individuals and other factors, is approximately 1.70 centimeters. But what does this mean from the visualization or focusing of image perspective? It means that whatever image we observe, or whatever object we observe, our eye has to be able to focus a nice converging ray image on this retina. If it's off the retina, it will look blurry to us. Just like looking at a projector screen when you don't have the projector focused. It'll look blurry unless you move the screen back and forth. But we can't move the screen of our eye. That distance is fixed. Turns out in a camera, that's what moves. You have a lens that moves back and forth. But with our eye, we can't do that. We literally have an adjustable focal point for our eye. So now, to estimate the focal length of a healthy eye, we can do this for any point on the eye. Let's think about an object out here at infinity. And all I mean is it's large compared to 1.7 centimeters and compared to whatever this focal length has to be in order to focus 1.7 centimeters away from it, the image.
We'll bring some parallel lines in.
And by the way, it also has to be tiny.
Have them invert and land on the retina.
It has to be really a really tiny image because our retinal region is very small. We're looking at large objects. We're bringing all that information in. We've got this tiny little image we're seeing in the back of our eye. So we've got this distance to deal with to the lens, your O distance. So if we assume 1 over Fi then is going to be equal to the sum of 1 over the object distance. So I'm going to say 1 over the object at infinity plus 1 over the image distance. And that image distance is, I'm going to use meters instead of centimeters now. And the reason is I'm going to make a translation to optical power. You'll see what I mean. 1.7 centimeters is 0.017 meters. Okay? It's a crappy number, but it's important to use meters here for what I want to do here. Okay? Now, because it's infinity, 1 over infinity is 0, which means that for an eye to be healthy, what it's functionally doing is it's focusing. The retina represents basically the focal point, the focal distance away from the eye's optical effective lens. So we take this number, we take the inverse of that. What do we get for a number, 1 over F? It's positive. It's going to be somewhere around 56. 58.8 inverse meters. We call that the diopter. And the only time you ever use the term diopter is when you're going to the optometrist. Or when you go in to buy a pair of reading glasses. The one thing I know for certain, whether you ever wear eyeglasses or need eyeglasses, at some point, it's kind of like death and taxes, you're going to need reading glasses. Unless your nearsightedness is just right to where your near point is close enough to your normal reading distance that you never have to wear them. You just take your glasses off and you'll need eyeglasses. So one way or the other, you will need eyeglasses during your life, whether you choose to wear them or not. You'll either need reading glasses because your eye can't adjust to closer objects, or you'll need glasses to see from a distance if you can make something out up close. Now, whether you choose to wear glasses, that's your own thing, but just because of the degradation of the eye and the nature of it, one or the other is going to happen no matter what. Take your pick. So this is the optical power of the eye. Now, just to give you a sense, when you go into an eyeglass shop and they say, I don't know, Brendan, do you know what your optical power is?
I have no idea.
No? You know what? Nobody reads these things. You get a prescription. Some doctor says you got a migraine headache. Here's your prescription. Do you bother to read it? 1.75. They usually do them in 0.25 intervals. And
Actually,
you're
I do know.
nearsighted, right?
Yeah.
Okay, he's nearsighted. He has eyeglasses that are negative 1.75. What are yours?
This one is 0.75 and this one 1.5.
1.5. So you have two eyes that are different.
Yeah.
Different focal point.
And I also
So-
have cylinder.
No, what that means is that's a negative number. What it means, you take that value of optical power, and by the way, to get the focal length, take the inverse of it. All you have to do to get the focal length is take the inverse. But think about this for a second. If you need to decrease your optical power by 1.75, right, negative 1.75, that means that if you had a healthy eye that should have this optical power, 58.8, your eyes are actually stronger than they're supposed to be. They've got a larger optical power. It's more like 60.5.
It focuses in front of the red. So that's what
Or another way of saying it is that you have a short near point. Anything that is at your not near point, anything at your far point, you focus right on your retina. So one of two different ways of looking at it. But yeah, your eyes are too strong. So when we think about people that have bad eyesight, it's because their eyes are actually too strong. And no matter how you relax it, you can't relax it to make it any lower than this. When we strain our eyes, we make our optical power even greater. But the most relaxed that we can see, this is why if you go to an ophthalmologist, they'll put those eye drops in to dilate your eyes. You know why they do that? They do that so your eye is relaxed. So you can only see at a distance. You cannot see any closer because your eye can't adjust. Your muscles are all numb. And so whatever your relaxed eye is, that's what it is, and it's a lot easier to deal with if you're trying to figure out what kind of glasses you need for a distance, especially if you're farsighted. If you're nearsighted, it doesn't make a hill of beans difference. But if you're farsighted, got to do it because effectively your far point is greater than infinity. That doesn't make any sense, but it's actually, you could think of it as being greater than infinity.
So,
You see beyond the stars.
they must take into account some kind of estimation of how far from your eye the pair of glasses is going to sit for every individual.
Oh yeah, they back it off a little bit or add a little bit extra. Well, with contact lenses, it's different. So with contact lenses, typically you're a quarter diopter lower than with your eyeglasses for that reason, because they sit right on your eye. And the assumption is, I think it's 1.5 centimeters away.
Okay.
They
Something like that.
measure the distance usually for how far your eye is.
Yeah, usually they don't. They don't even bother anymore because they mostly sit about the right spot. Unless you have really, really bad eyesight, they don't bother because your eye can adjust as long as it's overcorrected and not undercorrected. But that being said, they do measure your pupillary width. Call that your pupillary distance, your PD. And the reason is they want to make sure that you actually look at the center of your eye, because you have all kinds of aberration and prismatic effects if you look away. That's why people get, when they first wear eyeglasses, they get headaches. One of the reasons they get headaches is your eyes are used to doing this when you're looking. You don't look like that most of the time to see. You use your eyes. But if your glasses stay fixed and you use your eyes, then you start looking through abhorrent images off to the side, and then give you a headache. So that's why they typically measure that. Now they may measure this if somebody's particularly anal retentive, but usually they don't. They don't even bother. Because that's why they use plus or minus a quarter diopter, because there's sort of a built-in fudge factor. Okay? So if you were nearsighted and couldn't see all the way away, it's because this number's too high. You subtract from it with your big optical correction. If this number's too low, then that means you need a positive lens. You need a stronger lens just to see at infinity, because your most relaxed eye, if you will, sees beyond infinity. Or you see objects that are way, way, way far away, but they focus behind your retina rather than in front of it.
So is one lens nearsighted people converging and the other diverging?
You betcha, you betcha. But here's what makes it even funner. Regardless, the images that you see are always images outside your lens. They're always virtual. You never see a real image with your eyeglasses because you're still seeing things out in front of you. And they're upright, right? If a lens is producing a real image as one lens, it's going to be inverted. So all images that you ever see, whether it's converging or diverging, it's always going to be a virtual upright image.
Does it screw with your depth perception?
Not if you have two eyes, because depth perception is based on stereo vision for
Your
us.
eye does actually flip the image. Your brain flips it again.
Yeah.
No, your brain doesn't flip it. Your brain uses it, and its entire reference is upside down. So we say it flips it, but our brain doesn't care. It's just developed to look at an image however it comes in. Now, if it were technically right side up, your eye wouldn't know what to do with it. You'd be upside down. Right? So everything is just reference to our brain. That's sort of an evolutionary thing.
Yeah.
We're just used to seeing it that way. Believe it or not, if you were used to sitting upside down all the time, eventually you'd process that way. If you were doing handstands all the time, or you were, from the time you were a baby, just left upside down and you were looking at things and watching things come towards you, you'd see all right upright images of people coming towards you. Now, they'd be upside down with respect to you, but they would be upright images in your mind, and your eyes would be just fine. You'd adjust to it because your neural networks are programmed to deal with it.
Yeah, when you were saying that you never see a real image, is that true also for contacts? Is
Yeah.
it the same thing?
Yeah. Now, when I say that, now let me rephrase that. The final image that your eye processes is absolutely a real image because you have to have the light converging on something that can pick it up, right? Measure it, just like a piece of paper. So your final image is always a real image. But the image produced by a contact lens or eyeglasses is always, that first image is always virtual. But that's okay. It doesn't matter what the virtual image is because that light ends up processing through this second lens and makes a real image there. And if it doesn't, you're not going to pick it up. You won't see it. So all kinds of kind of cool things about it. So you got two choices. If you're nearsighted, we sometimes call it myopic. It just means that you've got an optical power larger than that. And if you're farsighted, it just means you have an optical power less than 58.8. And one of the things that if you never need eyeglasses to see at a distance, you'll need to get reading glasses to deal with things up close. Whatever this value is, this is Fi for the far point. In other words, this is based on the farthest distance you can possibly see. This is the relaxed eye. And by the way, if you notice, it corresponds to a focal length of plus 0.017 meters, 1.7 centimeters. You can think of it either way, but it's just easier to think in terms of optical powers. You don't have to do inverses. Now, by the way, if you're farsighted, think of the trouble that produces. How do you distinguish between somebody who has 20/20 really healthy eyesight because they can see the sharp craters on the moon, or a distant object really, really sharp, the letters at the other side of an optometrist's office, and somebody who's farsighted, whose all its eye has to do is strain in order to pick out those images, right? It's just like muscles. You can contract and contract to lift things or to increase your power output, your strength, but you can only relax so much. You can only go so flaccid, so to speak. So you're absolutely limited by your relaxed state. Then you can tense. And by tensing, it increases this number. increases this value, allows you to focus on things much closer, at least up to your eye's ability to do it, the strength of the muscles in your eye. Okay? So we've got a lot of little things going on here, and we'll talk more about this next week. But it's really cool. And so all of our dynamics that we deal with, and we see a lot of it around us, is based on this idea. And incidentally, if you look at an object up close, just a real quick calculation, your near point. What we call traditional reading distance is 25 centimeters. In other words, I'm going to pick something up. I want to be able to see it here without it straining my eyes. I want to still be able to see it. It's about 25 centimeters. That's what the optometrist uses to say, oh, you can see, or you don't need reading glasses. You may not be able to see up here. Believe it or not, infants can focus things right up here. And I guess since their food source is usually right there, that makes sense. But as you get older, that flexibility gets worse and worse and worse and worse. At some point, people have to do this to read. You see, like grandmas and them.
My dad's doing that right now.
Yeah. I'm starting to do that myself, and it's pissing me off. It's driving me crazy because all of a sudden it's starting to hurt. I can really strain and do it, but it's really starting to tire my eyes and make me tired to read long distance now. I can do it still, but I can't work with things up close. Like if I were trying to thread a needle or something, it's harder on her. But let's just look at this for a second. If, say you have an object at 25 centimeters, so let's just hypothetically say, I know we need to go, but that would be 0.25 meters. What does your eye's optical power, or focal length, either way, what would it need to be to focus on an object up here? Forget about infinity. That's just saying I'm relaxed, I'm going to see as far as I can see. But now think about what your eye would have to do, what has to change in order to see here. Plug it in the same value, right? Only now we've got 1 over O plus 1 over I, and that's going to be equal to this 1 over F. So now we've got 1 over F, and the optical power, we can deal with it. It's 1 over 0.25. By the way, that's 4. Plus 58.8 if it's a healthy eye. We already established what it should be at a distance, and that's what your object distance is anyway, right? Or your image distance. So once we know that number, we don't ever have to calculate that number again, by the way, because the inverse of the image distance is the same as the focal length of your healthy eye. In other words, you have to add 4 to this. Oh, 62, evidently I can't add. 62. In other words, your eye has to increase from here to here in order to see up close. You have to increase 4 diopters, or you take the inverse of that, change your focal length by that much. If your eye can't strain to get 4 out of it,
So
you're screwed.
focal length is
Then you're going to have to get
shorter.
some eyeglasses. Your eye's ability to go from here to here, that eye strain is called accommodation. And your eye's maximum ability to increase this value, whether it's to see something at 25 closer or farther away, whatever that closest point is that you can see in focus, you can fake it, and you can really see sharply, that's called your near point. So our eyes are dimensionally constrained by the farthest point we can see and the closest point. And a healthy eye should be able to see far, far distances away, infinity, and at least up to 25 centimeters, because then we're infinity. And when we have to start doing this, then your optometrist says, I need eyeglasses. And you go down to the store because you don't want to pay $150 for eyeglasses, and you buy a little set of reading glasses that are +1, +1.5, +1.25. That's next time you go into a drugstore, go just look, and when you pass in the reading glass section, just look at the values on it. Again, those are optical powers. Take the inverse, that's the focal length. That's it. But that's what your eye is doing. It's just giving an extra bump, because in order to see up here, you need 62, but you're only maybe getting 61. So you got to get +1 to take you over the top. Your eyes eye's gotta deal with everything from 25 outward, and so your eye's constantly adjusting. So if you've got 1.75 prescription, I suspect you probably can't see farther than a meter.
Oh, you're fuzzy right now.
Yeah.
I
Your
mean, this-
sharpest point is probably about a half a meter away.
Yeah, this football starts to get fuzzy.
Yeah, and that's a minimal eye prescription. Okay, you probably can see about a meter and a half away, meter and a quarter. I mean sharply. Now you can make out objects maybe to the wall if they're just the right shape, but to see sharply, 0.75 is hardly a prescription at all. I went a long time seeing 0.75, not even knowing it, until I couldn't see the sand cranes. It's like, oh crap, my eyes suck. It's funny, where we really start to notice it is not objects that are 100 meters away. It's usually when we're inside of 10 meters, and that's when we're starting to say, oh gee, I'm having a hard time seeing. Everything outside of that, for the most part, we don't deal with much, and I can kind of make it out, so it's close enough. I can see the 2 on that sign, so I'm good, even if I can't really see it sharply. But when you need eye correction, it means you physically can't see something sharply around a meter. Think about that when you see somebody who's walking with wearing eyeglasses. You can only see sharply a meter, give or take, maybe closer even. About a meter.
Yeah, I can get somewhere within a meter for them, but I can't see. People will wave at me, like if I'm wearing glasses, I can't tell who's waving at me.
I had a girlfriend that had really, really bad farsightedness when I was in high school. Like she wore Coke bottle glasses. She wore contact lenses when I was started dating. And one day she showed, I was over her house and she was in these big old Coke bottle lenses, +6 diopter prescription. If she took her glasses off, she could see everything fine. It's like, how can you have a +6? It's because her eye would have to contract, because it's +6, she was effectively seeing it like 52.8. But just using regular accommodation, she was using her reading ability to see distant objects. Her eyes would strain, but she could see just fine. We can't strain if you're farsighted, past relaxed. But she could, so it was really strange. It's like, how can you see and then say that you need eyeglasses? That's what I mean, that it's a problem when you go to the optometrist and you're farsighted. You can always strain and make out objects. So they deaden your eyes so you can't accommodate and bring it in, because distant objects are basically a reading phenomenon for somebody who's farsighted, hypermetropic. So they deaden it, so now they can't focus even at a distance. And then you have to adjust the lens to see how much do you have to add before that distant object comes into focus. But your eye will fake it if it's allowed to contract. Because that's all we do when we read, is see anything close, we just contract. All right, get out of here. Sorry for keeping you so long. It's just kind of an interesting story. It's so common. Is that why everybody's waiting?
Yeah.
Is it? I was thinking it was week 9. It's week 8. No, let's make it Thursday. We'll give you extra time. How about that? Is that reasonable?
Either way, I've got 3 exams next week.
I don't mind making it the following week, but I will say this. Optics and waves will be on this exam.
Not diffraction or.
We're not going to cover diffraction. Sound will be on the exam. But we're not going to have a chance to cover diffraction for this.
So what chapters are we covering?
You won't even see it in lab until next week.
17 and 30,
Today's the lens, tomorrow's the lens lab.
34, 34, 5.
Did you have lens lab last week? No, you had
34 and 35. I'm 17.
So this week is lenses, because you missed that lab. And next week will be